In today's lecture, we will discuss about the interconnection of three-phase systems. So this lecture will cover the types of interconnections of three-phase systems. Then one of the type of three-phase systems, which is star-connected system. Then we will see the equations for the voltages and current which are associated with the star-connected three-phase system or star-connected supply system. Now to start with, the first is let us discuss about the various interconnections of three phases. Now, as we have already discussed in our previous lectures that three phase means three voltages and their three currents. Now, these three voltages are separated or placed from one another at an angle of 120 degree from one another, right? So now we have already discussed that a single phase system can also be used as a three phase, but in that we need to have three different single phase systems, and then we can use them as a three phase system. So that would increase the number of conductors, number of coils, and number of wires. As you can see in this particular diagram, we have a 6-wire connection of three phase system. This means all these are single phase systems and they can be used as three phase by in a separate way. Okay, now this is a disadvantage to the system which is used in this particular manner, because in this particular arrangement of the windings and coils and load, this is load basically here, this one is load. So that means now that means we are using more number of wires, we are using more number of conductors. So this would lead to the increase in the overall cost of the system. And also because the wires are more wires means more transmission losses. Arrangement is basically quite complex arrangement, complicated arrangement, and it is also expensive. So this complexity and expensiveness of this arrangement, which is used as a three-phase arrangement, is reduced by reducing the number of wires. So this can be done by using any of the two methods which are mentioned here, the star connection and mesh or delta connection. Star connection is also known as Y connection. Mesh connection is also known as delta connection. So these are the two types of three-phase systems which are generally used in power systems for generation of electricity, transmission or distribution, right? So they have certain advantages over the 6-wire connection of a three-phase system. Now, let us see these two types of systems through a diagram. As you can see in these two diagrams here, this is the star system and this is the delta system, right? Now, why we call this as Y connection? Because you can see here, this is something like this. The three coils are placed to one another and they are forming a Y, or like this. Okay, if you reverse this one, you'll get a Y here. Now, why we call it as a delta? You can see this is forming a delta shape, right? So that is why it is called as delta connection, or this is also known as mesh connection. Why? Because this, as you can see here in this particular diagram, it is forming a mesh. It is a mesh. Now you know that mesh is the elementary loop of any electrical circuit, right? Now let us understand this in detail. Now, because this is a star connection, it has three windings. Winding this one A, and then it is B, and then this is C. Okay, you can see all these windings are placed to one another at an angle of 120 degree. Now this ER is basically the RMS value of the EMF induced on this particular winding A. Similarly, EB is the RMS value of the EMF induced on this winding C, and EY is the RMS value of the EMF induced on this winding or coil B. And because the standard notation that we use is red, yellow, and blue. So the line blue is connected to the phase C, line yellow is connected to phase B, and line red is connected to phase A. So these are three phases: phase 1, then this is, let us say, phase, let us say this is phase A, this is phase C, and this is phase B. Or you can also say this is phase red, phase yellow, sorry, blue, and phase yellow. So you can use any notation for this particular uh, connection. You can also see one dotted dashed line here, which is called as neutral wire. Now this neutral wire is used to return, it provides returning path to the current, right? So this particular system, this one is a three phase four wire system. So that means here you can see we have two wires less than this particular system. Here we have six wires, here we have four wires only. So three wires are phase, this is phase A, this is phase B, and this is phase C, and one is a neutral. So it has three phases plus one neutral, so it has four wire, and so we call this as three phase four wire system, right? Now let us come to the delta shape, delta connection. Here, as you can see, we have three windings, and if you see their electrical angle, these windings are also having a 120-degree phase shift, right? Now the same is here also. You have phase A, you have phase B, and you have phase C, right? And these voltages are basically the RMS values of the voltages which are induced on the respective windings, okay? And we call these voltages as generally phase voltages. So now here we have three wires, we do not have any neutral wire here, no neutral, right? So because there is no neutral in this particular case, so it is a three wires, or you can say it is a three phase three wire system, right? So three phase three wire system. Now let us come to the star connected system. We will understand now what is a star connected system. As we have discussed, a star connected system is basically a three phase four wire system in which we have three phases and one neutral wire. Okay, now if we do not put the neutral wire, so it becomes three phase three wire star connected system. If we remove the neutral wire from here, so we have only three wires, so it is a three phase three wire star connected system as shown in this particular diagram. Now there are certain things that we need to understand about a star connected system. The first is that what are the phase voltages and line voltages, because we will require this during the derivation of the equations associated with this type of system. And then we need to understand what is phase current and line current, right? Now, now what is the phase current? Let us come back to this particular diagram here. Now, because this is one phase, this is another phase, and this is third phase. So any voltage that is induced on this particular phase is the phase voltage. So this is the phase voltage, right? This is also the phase voltage, and this is also the phase voltage. Now, why are these phase voltage? Because these voltages are induced on the winding, and winding we are calling as phase basically, right? So this is the phase voltage, or you can say any voltage that is between the neutral and the phase is the phase voltage. So we'll say that a phase voltage is voltage between phase and neutral, or you can say line and neutral, right? So a phase voltage is also known as line to neutral voltage. So So here you have this one. Okay, so we will call it as, let us say, V A N. Now you have to remember the two subscript notation here. Now what is this V A N? So that means the voltage direction is from N to A. So similarly, we will have the voltage between the neutral and phase B. So this is V BN, because the voltage is from N to B. So this is another phase voltage. So neutral to line. This is line. This is line. And this is also line, right? So now let us come to the third. So in third one, we have, so this one, this is a neutral, and this is phase C here, C here. So we have this one, like, so this is VCN. So it is from N to C. So this is a third phase, right? This is also phase voltage. So the phase voltage is basically the voltage that exists between the neutral and the line of a star connected system, or a three-phase system, you can say, right? Because we do not have neutral wire in the delta. In delta we don't have any neutral wire, so we don't have this definition for the phase or line voltage in case of delta, right? So because we have a neutral wire here, so we will say that the voltage that exists between a neutral and a line in star connected system is known as phase voltage. And there is a reason behind it, and the reason is that the phase exists between the line and the neutral. So here we have one phase, here we have one phase, and you can see neutral and line, here we have one phase. So this neutral is the common point, basically it is a junction. Okay, right? Now let us come to the uh, phase line voltages, sorry, phase voltages we have seen. Now the voltage that exists between line to line, two line. So this is one line, this is another line, and then we have a third line here. So third line is this one, right? So there are three lines basically. So we have, this is between A and C, or you can say this is between R and B. So this one is VRB. So now because the direction can be from B to R, blue to R, so the direction will be something like this. So this would be the direction in this case. Similarly, if it is from Y to R, so the direction is V R Y. So Y to R. Similarly, if it is from Y to, or you can say B to Y, so it is V Y B, or B to Y. Or it can be, if it is like this, so it is V B Y, because it is from Y to B. So now this V R Y or V B Y or V RB, because these are line to line voltages, and hence we call them as line voltage. Okay, so the voltage difference between the two lines, or you can say the potential difference between the two lines, red line, yellow line, and blue line, is known as line to line voltage or line voltage simply, right? Now let us come to the next thing, that is the line current and phase current. Now line current is the current that flows in the line. Let us say this is IR, this is IY, and this is IB. And here let us say it is neutral current IN, which is equal to IR plus IY plus IB. And that is why we call that neutral point, or neutral wire provides the returning path to the current. Now the current that flows in the line is the line current. This is the line current. This is the line current, and this is also the line current, and this is also the line current. Now the current that flows in the phase, this is, let us say, A N I N A, from N to A. So this is the phase current. This is I N C, from N to C. This is, let us say, I N B, from N to B. So the current that flows within the phase is known as, so these all are known as phase currents. So in case of a star system, the same current will flow through the line, same current is flowing through the line. So we will say that phase current is same as that of line current. So phase current is equal to line current in a star three phase system. This is what we need to understand. So let us come back to this slide, and the same thing is mentioned here. The phase voltage is nothing but the voltage between any line and a neutral point is known as the phase voltage, or you can say the voltage that is across the winding is known as phase voltage, and the voltage between any two lines is known as line voltage, or you can say line to line voltage, right? So similarly, we have phase current. The current that flows in the phase is known as phase current, and the current that flows in the lines is known as the line current. Now, what are the lines? This is a line. This is a line. This is a line. This is a phase. This is a phase, and this is a phase, right? So this is what we have. So as you can see here in this particular diagram, we have three phase voltages: En, EYN, ERN, EYN, and EBN. So there are three phase voltages, and here you can see the voltages from N to R, voltages from N to Y, voltages from N to B, right? So this is the phase voltage, and we have three line voltages: VRY, VBR, and VYB. Now the direction is from Y to R. You can see it is from Y to R, and here direction is from R to B. The direction is from R to B, and direction is from B to Y. It is like this. Okay, so there are three phase voltages: ERN, EYN, and EBN, and there are three line voltages: VRY, VBR, and VYB. These are the line voltages. Now, let us come to the current. As you can see, the current that flows in the phase is the current that is flowing in the line. Same current. So, this is the line current and this is the phase current. This is phase current. This is line current, right? Similarly, here also you have this current IY, which is same as flowing in this line also, and IB is flowing in this particular line. So here we have three phase or line currents. These are IR, IY, and IB. Now RYB is the notations taken from here: red, yellow, and blue. Now let us come to the voltages and current that are associated with the delta star connection, Y connection basically. As we have understood that there are three phase voltages in this type of system, and there are three line voltages basically. So these line voltages are basically the phasor algebraic sum of these two phasors, because it is also a phasor. So it is the algebraic sum of these two phasors. So VRY, that means the voltage between line this line and this line is VRY. So red and Y. So it is the phasor difference of the phase voltage here and the phase voltage here. So this is the phasor difference basically. Similarly, the voltage between the line Y and line B, right, is VYB, which is the phasor difference of the two phase voltages associated here. As you can clearly see that there are two phases here, this one and this. If you apply KVL in this particular mesh, if you apply KVL in this particular mesh, you will get that VYB is equal to EYN minus EBN. So these equations have been obtained by applying KVL in each loop, right? So here, if you apply KVL, so if you apply KVL in this way, so you can see, you'll find VRY is equal to this minus this. Similarly, when you apply the KVL in the uh, third loop, basically, third loop is this one, this, right? So you will get one. This is the first loop, this is the second, and this is the third outer one. So you will get VBR. So you can see this one, VBR is equal to EBN minus ER and this one, right? So you need to see these as three different loops. So by applying the KVL in each loop, you will get these three equations. So what does it mean? It means that VRY is the resultant of these two voltages. Similarly, VBR is the resultant of these two voltages, right? And the same is with this one also. It is VYB is also the resultant of EYN and EBN, right? Now, if we have to draw their phasor diagram, how will we draw? So the phasor diagram is already shown here in figure number 6. But let us see if we have to draw this one, how will we draw? The first thing that you will do is draw the uh, phase voltages first, right? So first of all, what you will do is you will draw the phase voltages. So because there are three phase voltages, so the first phase voltage is, let us say, um, so you can draw it like this. So this is one way of representing. I am showing it in a different way. So let us say this is E, Y, N. This is, let us say, your E, R, N, and this is, let us say, your E, B, N, right? So these three are the phase voltages. Now, if you draw this EBN, sorry, if you draw this EBN backward, so let us draw it backward. So here, let us draw it like this. So this will become minus EBN. Similarly, if you draw this ERN backward, so it will become minus ERN. So similarly, if you draw this backward here, so it will become E minus EYN like this, right? Now let us come to the third part, which is the resultant one. So let us take this one. Now, as we know that VYB is the resultant of EY and EBN, minus EBN, right? So this is minus EBN, this is EYN, and the resultant is here. So this is your VYB, right? Similarly, the resultant of minus EYN and ERN is equal to VRY. So let us draw this also. So it is this one. So this is VRY. And then we have the third one, which is the sum of these two minus ERN and EBN. So let us see where it is. It is minus ERN, EBN, and the resultant is here like this. So this is VBR. So this is how you can draw the phasor diagram. And this is what is shown here in this particular diagram. You can see EYN is one phase voltage, 120 degree apart from EYN. You can see clearly 120 degree apart from EYN, you have ERN, and 120 degree apart from ERN, you have EBN. So these three voltages are at 120 degree phase angle from each other. Now, if you draw this EBN in backward point, so you'll get minus EBN, right? And if you draw this ERN as backward, so you'll get minus ERN. And similarly for EYN, you'll get minus EYN like this. So the resultants are VYB, VRY, and VBR. So these are the line voltages. And this is the phase voltage, phase. And this is also the phase. So this is how you can draw the phasor diagram of the uh, star connected system, which has all the three phase voltages and all the three line voltages, right? So now let us come to the derivation of the equation. So let us see what is the relationship between a line voltage and a phase voltage in a star connected three-phase system. So this is very easy in this particular case. You can make out this from the this particular diagram here as shown. Now here, if you see, now this angle is basically the 60-degree angle, this one. This is 60-degree angle, right? And the angle here is 30-degree between line voltage and a phase voltage. The angle is 30-degree. Here also it is 30-degree. Similarly, here also it is 30-degree. So let us see how it is calculated. Now, the two phasor ERN and EYN. We have taken two phasors here, ERN and EYN, this one, these two phasors, and we have tried to calculate the value of ERY. Okay, so it is equal to, because these are equal in magnitude. Why they are equal in magnitude? Because they are equal in magnitude because it is a balanced system. It is a balanced system, and we have already seen what is a balanced system. The balanced system is the one in which all these voltages, the phase voltages, will have same magnitude, and separately the line voltages will have same magnitude, right? So a balanced system is one in which V E N VRN, sorry, is equal to the magnitude of VRN is equal to the magnitude of EYN equal to the magnitude of VBN, and this is phase voltage, right? Similarly, the magnitude of VRY is equal to the magnitude of VBR is equal to the magnitude of VYB, and these are the line voltages VL, right? So this is a balanced system. So the any line voltage is basically the phasor difference of two phase voltages, right? Phasor difference of two phase voltages. So we can simply use the phasor sum or the phasor algebra in this particular case, and by using phasor algebra, we will get that it is equal to EPH, where EPH is the phase voltage basically, right? Cosine of 60 by 2, because the angle between any phase voltage and the line voltage is 30 degree. So it is 60 degree by 2 NEP. So it is 30 degree. So it is root 3 into EPH, right? Now similarly, VYB is also, because it is the phase sum of these two phase voltages, and so it is equal to under 3 EPH, and similarly this one. So we can conclude here that the line voltage in a star connected system is equal to root 3 times of the phase voltage, or line voltage EL is equal, not EL basically, because EL is not induced here. So VL is equal to root 3 EPH, right? Why we are using EPH here? Because this is the induced EMF. The phase voltage has been induced here. Here in these windings, phase voltages are induced in these three windings, right? So this is the relationship between the phase voltage and phase uh, line voltage in a star connected system. Let us come to the relationship between line current and phase current in star connected system. As you can see, the current that flows in the phase is the current that is flowing in the line. The same current is flowing in the line. So we will say that here the line current is equal to phase current, right? And the phasor diagram is shown here because every phase current, its phase voltage is ERN, right? So because this is an inductor, this is an inductive circuit, right? Now because this is an inductive circuit, so what will happen? This IR lags ERN by phi. So ERN is the voltage at this phase, EBN is the voltage here, and EYN is the voltage here, right? So similarly, you can see here that EIR is lagging ERN by phi and the phi. So the same diagram can be drawn here also in this one. You can draw the same thing here also. Okay. What you have to do is, now what is the current of EYN? Let us see. EYN current is nothing but it is I, this. Let us say it is IY. Okay. So the notation used is IY. Okay, same. Right. So from here, EYN take 5 degrees. Only 5 degrees, nothing else. 5. So draw IY. Now from here, take 120 degree. Take 120 degree and draw ERN. What is the current here? IR, right? This is the current. So draw IR. From here at 120 degree, here at 120 degree, draw EBN. What is the current of EBN? EBN's current is here, IB, right? So draw IB. So here also you can draw, the phase difference will be 5 in every case, 5 degree, 5 degree, 5 degree. So the same thing is shown here in this diagram. You can see this is the phase voltage, this is the phase voltage, this is the phase voltage, and this is the phase current, and phase current. Because in a star system, phase current is same as that of line current. So we are using the same notation here, and you can see the phase current is lagging the phase voltage by 5 degrees, right? Now, so this is a summary basically. So in a three-phase star connected system, line current is equal to phase current. All the line currents are equal in magnitude, but they are displaced at 120 degree from each other. That is inherent characteristic, right? The angle between the line currents and corresponding line voltages is 30 degree plus minus 5. You can see here, this is the line voltage and this is the phase current, right? And the angle between them is 30 or plus minus 5, right? So this is what we have written here, right? Plus if it is lagging, as we have already discussed this one, positive phase angle plus phi means lagging and minus phi means leading. So in our last lecture, we have discussed this thing. Now this is the power associated with a three-phase star connected system. So total power is, because it is a balanced system, right? So power in each phase into 3. So power in each phase is VPH into IPH, where VPH is the RMS phase voltage and IPH is the RMS phase current, right? So VPH, IPH cos phi. So we know VPH is nothing but VL by root 3, because this is what we have seen here, right? So VPH is VL by root 3, right? So the same thing is used here. IPH is equal to IL, right? So by putting these values here, you'll get this equation. This is the active power, and the reactive power will be the same but sign component, and the total power is this one. This is the total power that is associated with a star connected system. And as we have already mentioned that the neutral current, so somewhere we mentioned in this lecture, neutral current, this one, okay, neutral current is the sum of all the three line currents or phase currents, you can say. So it is equal to this one, right? And by using the power triangle concept S, P and Q and phi, so you have this one for a star connected system, and power factor is same. So power factor and this remains same as that with the single phase circuits, right? So this is it for today's lecture. Thank you so much.